Hello, welcome everybody. We are here for another Continual AI seminar session. And today we are with Andrés Villa from Pontificia Universidad Católica de Chile, if I'm pronouncing it correctly, and King Abdullah University of Science and Technology, also known as KAUST. And he's going to talk about the paper which just got accepted as CVPR this year as oral, titled vCLIMB, a novel video class incremental learning benchmark. So the title says much, but not everything, I think. So I'll just leave the stage to Andrés. Please, the floor is yours.
Okay, thank you, Andrea. Hi, everybody. First of all, I want to thanks to Continual AI team for the invitation. I'm Andrés Villa, a remote research intern at KAUST University. I'm pursuing a PhD in computer science at Pontifical Catholic University in Chile. So in this presentation, we talk about vCLIMB, a novel video class incremental learning benchmark. It is a word accepted as oral in CVPR 2022, done with Comel, Victor, Fabian, Juan, who is here, and Bernard Ganel. Okay, deep neural model for human action classification are typically trained on a large-scale dataset to achieve a state-of-the-art performance. However, they cannot handle instances from novel class. This is very likely to happen in a real-world application due to the huge action diversities. Therefore, a real-world deep learning application rarely involves a single training stage. Instead, this method could require a sequential training in a set of independent tasks without forgetting. However, it is challenging because the current models have a high plasticity, and the most used training strategy is to train the whole models on the set of data distribution. So the models forget those learned previously. Therefore, it is necessary to train the model in the data of the current task plus the previous learned task data. But it is not viable to save all data due to the legal and technical constraints. Under this condition, it is essential to enhance a balance between the stability and plasticity in neural networks like human beings do. But what do stability and plasticity mean? Stability is the ability to reestablish or remember the activation patterns needed to solve a task. For instance, here, the model doesn't change its parameter while training on the sequence of tasks. So it is good to remember, but not to learn new knowledge. However, plasticity is all the opposite. It's the ability to establish new synaptic configuration, which is essential to learn new tasks. This problem of learning sequentially without forgetting is known as continual learning. In our work, we focus on the most challenging setup of continual learning, which is class incremental learning, where the label and data are mutually exclusive between tasks. Training data is available only for the current task, and there are no task ID available during training and inference stage. It is this last idea is very important because when the task ID is available, we have a more straightforward scenario called task incremental learning that allows learning a model which does specific components, but it is not our case. But we can use this setup for this task also. Most of the existing works that address the class incremental learning problem were done for image domain. They could be divided into groups, the regularized method and memory-based method. The regularized-based method penalized the abrupt change in the most relevant parameters learned from previous tasks. In this group, we have models like EWC and MIS. The difference between them is the way they compute the parameter relevance. For example, EWC use the feature information matrix, and MIS follow a self-supervised approach by measuring how small changes in the parameter affect the output of the model. In the second group, the memory-based method, the model mitigates the catastrophic forgetting by saving a limited amount of training instances from previous tasks. In this category, we have ICAR, for example, and BIC. ICAR is the most adapted baseline. It's combined rehearsal and distillation strategy, and also it follows this strategy to save an instance in the memory after training with the task end. It selects the almost relevant instance per class according to how close they are to the class prototype. On the other hand, BIC augment ICAR with a bias correction layer to mitigate the imbalance between the large amount of data for the new task and the relatively scarce data for previous tasks in the memory. Despite the growing interest in continual learning in image domain, the first 3 words to report results on video data were only recently published. Xiao et al. Proposed a spatio-temporal knowledge transfer strategy to mitigate the catastrophic forgetting. Park et al. Estimate the subset of feature channel that contribute the most to prediction of the previous task and introduce a temporal mask that keep this subset stable by learning new tasks, like something like a regularization. It also included distillation loss. Finally, Matt et al. Also approached this class incremental video classification problem by regularizing the feature space in the consecutive task. However, as you can see in this table, this approach defines different evaluation protocols, which are not available, making the comparison difficult. Likewise, they don't explore a realistic setup with untrimmed videos, which are common in real scenarios. Moreover, most of these setups leverage a set of classes of the same data distribution as the training, making it difficult to disentangle the effect of catastrophic forgetting, because some of these leverage this big pre-training to distill the knowledge for the next task. Considering all of the above, video class incremental learning comes with this unique challenge. First, this is not available protocol with the standardized tasks to train and evaluate methods. This makes the research process in continual learning for video understanding difficult. Second, like we have a memory constraint, and the videos and the video methods don't use the whole frames for videos. It is not viable and scalable to store full resolution videos on the rehearsal methods memory. Third, the video class incremental learning methods have to mitigate the forgetting while also integrating key information from this temporal dimension. Finally, often in real application, the video are not trimmed. Therefore, it's necessary to consider them for for class incremental learning tasks. To directly address this challenge and limitation, we propose vCLIMB, a novel benchmark for evaluating continual learning in video domain. It brings three main contributions. First, a standardized benchmark for continual learning in video action recognition. To do this, we focus on selecting challenging and widely used video datasets like UCF 101, Kinetics 400, and ActivityNet to create continual learning setups. We also standardize the evaluation metrics and define the memory of rehearsal methods in terms of the number of frames. This is the set of the tasks that we propose. As you can observe in this table, we define training and evaluation protocols on three well-known and challenging datasets, like UCF, Kinetics, and ActivityNet. We don't assume that any pre-training is available. We use the diversity of video in ActivityNet to provide two subsets, the ActivityNet trim, in which every part of the video when an action happens is considered as an independent video, and ActivityNet untrimmed, which is more challenging, labels a whole video which is more representative action class. Regarding the metrics, we select the most used metrics and to evaluate continual learning methods, which are final average accuracy and backward forgetting. We take their definition for the work Gradient Episodic Memory for Continual Learning by Lopez Paz et al. The final average accuracy measures how much the model learned at the end of the sequential training. It computes the average classification accuracy of the model evaluated on all learning tasks, including the last it was trained on. On the other hand, backward forgetting measures how much the methods forget from previous learned tasks after training the task E. Those the backward forgetting after learning the task A consider the difference between the original accuracy and the accuracy at task A of previously learned tasks. It is important to know that both metrics are complementary. We encourage to use both of them. Moreover, it is desirable to have high and low values for final average accuracy and backward forgetting respectively. Moreover, we redefine the memory in terms of stored frames instead of stored videos for several reasons. First, the video have different amount of frames. For instance, ActivityNet videos have much more frames than the other, for example, than the videos on ActivityNet, the videos on UCF or Kinetics. Second, memory constraint make it not viable to store full resolution videos. Moreover, not all frames are required to understand a video. We can save only the most relevant frame per videos. Third, we want to be first with the image methods. This opens important question like how can the most relevant frames be selected, and if it is better to have more videos with fewer frames or fewer videos, each one with more frames, for example. Our second contribution is we extend and evaluate for baseline methods. For from the image domain into the video domain. These methods are those I mentioned in the related work section. So this table presents the results of the baseline methods in the proposed setups, considering the ideal scenario when the whole videos can be stored in the memory. Consistent with image class incremental learning, the regularized base methods, EWC and MIS, lag significantly behind reply-based methods, regardless of the difficulty of the dataset or the number of tasks. Yeah. Moreover, we add a simple version of iCar, which we call naive. It selects the video for the memory randomly instead of following the iCar strategy. To compute memory size in terms of frames, we use the same instance per class radio as iCar, which is 20 when the model has learned all training stage, all training classes, excuse me. Those in the case of kinetics 400, which has 400 action classes, the maximum number of video in the memory is 8,000. Therefore, our frame memory size equals the maximum number of video in the memory by the average number of frames per video in this case. Surprisingly, no memory-based approach is superior across all video datasets, while the naive baseline outperforms the other baselines on UCF. iCar and VIC are better on kinetics and ActivityNet. Due to the space constraints, I cannot put the UCF results, and also the another reason is that the results obtained for UCF for this task is almost on par with the accuracy report for training TSM with the whole dataset at the same time. By the way, we use the TSM method as a backbone for all of these methods. Moreover, we observed that the longest sequence of tasks, in our case, 20 tasks, is a more challenging setup where the average accuracy is always lower for any method on any of the three datasets. Regarding our last contribution, we present a novel strategy based on consistency regularization that can be built on top of any memory-based method to reduce memory consumption while also improving performance. This figure illustrates the pipeline of our memory-based class incremental learning setting. After completing the training on the first task, the model has the option to select a few temporally downsampled videos to store in the memory. So when the model is trained on the next task, it must handle both the new video and the subsample and the temporally subsample version of those videos from the previously learned classes in the memory. Those to better remember previous tasks and reduce the drift between the samples stored in the memory and the original samples used at training time, we introduce a regularization loss represented by the dashed arrow in the figure, during the training phase of every new task. This loss, called temporal consistency loss, constrain the network to estimate similar feature representation for the original video clip and the temporally downsampled version of it. I have to clarify that this downsampled version that we use is the same that we are going to save in the memory. So if you select, for example, A frames uniformly from the video, you have to save into the memory. You have to use the same version to follow this strategy during the training. So the idea is that we can learn the same representation for the full version for the full resolution version of the video and the downsample version of it that we are going to save into the memory. This table compares ICAR with and without temporal consistency on the 10 task string action recognition setups, saving 4, 8, 16, and all frame per video. On kinetics and ActivityNet, our temporal consistency loss significantly improved the performance of ICAR when whole videos cannot be saved. Indeed, on kinetics and temporal consistency enable us to store as few as 4 frames per video and yet achieve more than 3% accuracy improvement over storing full videos. Likewise, we observe even more sizable improvement on ActivityNet trim. For instance, adding the regularization term with a model that have access to the memory consistency, to a memory consisting of 8 frames per video result in massive 24% improvement. Our results show that our method is more relevant for datasets that require more sophisticated temporal reasoning, like ActivityNet. However, on UCF, the performance remains almost the same, where the number of frames varies, and the temporal consistency loss does not help improve the performance. This is unsurprising for 2 reasons. First, class incremental learning on UCF is already not that much more challenging than training on the whole dataset in one task. One second, class incremental learning with the memory buffer on UCF is invariant to the number of frames per video stored in memory according to the first half of the table. This can be explained by the strong scene bias exhibited in UCF. Therefore, we recommend using this dataset for prototyping video class incremental learning methods, not for evaluating them. We perform a set of experiments to evaluate the realistic class incremental learning scenario with untrimmed videos and make a few interesting observations. First, ActivityNet untrimmed is more challenging than ActivityNet trim, as is expected. ICAR baseline achieved very improvement on ActivityNet trim, regardless of the number of frames per video stored in the memory. Second, our temporal consistency regularization improved by large margin in both ActivityNet setups. In conclusion, first, we propose and analyze vCLIMB, a continual learning benchmark for video class, for video action recognition, Second, we expose and tackle the unstudied accuracy drop experience by memory-based video class incremental learning methods caused by frame subsampling. Third, we present the temporal consistency loss to significantly alleviate the accuracy drop in trim and untrimmed scenarios. So, thank you very much for your attention.
Thank you very much, Andres, for this very interesting presentation on vCLIMB. And I really like the idea of videos in continual learning. I mean, there's the possibility to merge different modalities, like the temporal one, the spatial one. So lots of work that can be done in this direction. Also by exploiting the amount of work that we already have on images, right? So yeah, I think it's very interesting as a direction. Just one question maybe before opening the stage to the others. So as usual, we are live on YouTube, so feel free to type your question on the live chat on YouTube, or if you are here on Teams with us, you can just open your mic or write in the chat. So as a first question, maybe just a recap of your experimental setup. So which network did you use in your experiment? Because if I recall correctly, is the same, right, across all the data sets that you used. So the kind of networks, and if you train it from scratch, or you use a pre-trained network, maybe on another data set, which is not the videos ones, which was the problem of some related works at least. Yeah, let's start with just this brief recap on the model that you used.
Okay. For all the model that we extend from for images to video, we use the TSN backbone with the ResNet 34. This network use a temporal augmenting strategy in which we select different frames for the video during the epoch. For those who are not familiar with this method, this method divide the video during the training, divide the video into a segment, and take randomly one frame for each segment during each epoch, and the number of segment depends on the number of frames that you want to use. So it is like a temporal augmenting strategy, a temporal data augmentation strategy. And this method, we take this method from ImageNet. We use pre-training of images of ImageNet.
Yeah, makes sense. Thanks. So, and let's say I have a video dataset, maybe a dataset which is not public, or another one with respect to the.
Excuse me, Andrea, can you speak aloud?
Oh yeah, sorry. Can you hear me?
A little better.
Okay. Let me just quickly check my microphone setup in case it went down unexpectedly. No, doesn't seem so. But no, my question was just, can I take another video dataset, any other, and maybe exploiting your code, or I don't know if there is already a code base online, build a vCLIMB-like benchmark out of other video datasets at the moment?
Yeah, it is a good question. By now, we just can use the data set or the split that I explained before. We wanted to be fair with all of the experiment. We wanted to have the same split for all experiment, and we give the split that we use for the whole for the experiments, and also the problem here is the diversity of actions, because in video action recognition we have different type of data sets for the same task of action recognition. For example, data sets like UCF are very different for example, fine-grained video datasets like something, for example, or Epic Kitchens. So they analyze that they analyze that the experiment must be different in this case.
Yeah, makes sense. Thanks. So is there any question from the audience?
Now it's better. I don't know what you I don't know what you did, but now it's better.
Actually, nothing, but I'm glad that now it's better. Okay, maybe I have another one actually, so I can just take the opportunity and ask you another question about the downsampling. So,
okay.
Which policy did you use to downsample the video? So it's like taking one frame every k frames, or is it something different?
Yeah, the policy that we follow is a very simple policy. We take we sample the video uniformly. So we take 8 frames around the, for example, we take 8 or 4 or 16 frames around the video uniformly, and that's all. But we wanted that more project or that more person works in this policy. We want to open this line of research to select, for example, how we can select the best frames for to save for the video in the memory. It is a big open question now. What is the best policy in this case?
Yeah. I think it's an interesting aspect that might be explored, yes. Any other questions? Okay, in case not, we can thank Andres for the very interesting presentation on vCLIMB. I really hope to see, other works along this line, and I'm sure I will, because videos are for sure very interesting for continual learning. So thank you again for your time, Andres, for being here with us today. Just as a final reminder to everyone, feel free to join the ContinualAI organization. Very recently now, we adopted like the official membership of the organization, so you can choose and become a member. You can just visit the continualai.org website, and there is a join us section, and you can read there what to expect from us if you join the organization. So apart from that, I think I'll see you all for our next ContinualAI seminar, which is happening as usual in a week. And the spoiler alert, we will hear from Adrian Popescu about his paper on memory-free incremental learning. So, it promises to be a very interesting talk too. So let's meet all there next week. Bye.
Bye. See you. Thank you. Thank you.